Sala, and in this video we are going to discuss the problem statement and the interpretation of model fitting for classification, let's say when the desired model output is a yes-no response. In a previous video we discussed the deterministic interpretation of this kind of problems. In here we'll briefly review that and discuss the probabilistic interpretation of them. A classification problem had some inputs, x, which could be categorical or numerical, and we had the binary output y to be predicted. Will the student pass or fail the exam? Is this a picture of a dog or not? Then, in a deterministic interpretation of the classification problem, we would like perfect classification if possible. So my goal in a deterministic way with perfect classification was having a sensible decision threshold with a simple enough function, this thing instead of this thing, so that it classifies my samples. But if my function was not flexible enough, for instance with a linear classifier, then errors are unavoidable, and usually my model fitting will try to minimize the sum of a loss function that takes the value 0 if my model prediction 0 or 1 is identical to the training sample, and we must minimize the loss for the 1-0 mismatch versus the 0-1 mismatch. So I may consider in a different way being wrong in a red sample than being wrong in a blue sample. So well, posing this kind of loss function minimization, I would be able to obtain the optimal value of theta 1, theta 2, and theta 3. But okay, what happens when I am trying to predict whether a student will pass my control course? For instance, in my student stuff, I may have as information x the number of hours he devoted, but passing or not passing has many other uncertain components into it. The student may be nervous, the student may have a high intellectual capacity, so he needs less study time than the average student, or the student may have some psychological problem, so that even studying 400 hours he fails. So we have lots of non-controlled variables intervening in my problem, and then the approach to that problem is better done in a probabilistic statistical way. So in the probabilistic approach, we assume that my problem is random, and when we are discussing how to fit a model with adjustable parameters theta, then instead of requiring a binary output of my model, I will require a numerical output in the whole interval 0, 1, not in the discrete either 0, either 1 binary output case we were considering up to now. So this no, and then I would be happy if my model outputs, let's say 0.75. Because which is the interpretation I give to my model? Well, my new interpretation of my model output will not be a dog not dog result, but a probability of being a dog. But okay, that's wrong. I mean, a picture is a dog or not. We have no uncertainty. I have bad classifiers, but I have no uncertainty in the outcome. But in the pass-fail examinations, then I have uncertainty in my outcome, so perfect output is impossible. So when I tell, for instance here, that my model in which I have study time of my students and then the probability of passing, then my model tells that f of 80 is 0.79, what formally means is that the probability of passing subject to study time equal 80 hours is 79%. So we interpret my model output as a conditional probability. And then we seek such model output to be numerical between 0 and 1. Of course, also for the probabilistic output, we have a trivial solution. Rote learning will be, the probability of passing is 1 for students that passed, and the probability of passing is 0 for students that failed. But hey, come on, that's useless. It's the most true, the most certain assertion I can make, but that's useless for me. I want somehow a simple rule saying that if you study more than 100 hours, you will pass my examination with a 95% probability. So this trivial solution is trivially perfect but useless. So the shape of f must be somehow sensible, must be smooth, or I am not too happy on this shape of f. I expect a monotonically increasing probability of passing as time of study increases. So, I need to simplify my model structure and try to fit that. For instance, this blue probability of passing score was obtained applying logistic regression to this set of samples. And well, what is logistic regression? Well, they are sort of shapes that can be justified in terms of some odds or normal distribution or whatever. We have logit, probit shapes, whatever. But, in my case of passing students, well, I wish a monotonic stuff, and I wish to decide whether this is the probability or this is the probability, or maybe this is the probability. Sharp increase, because, once you do one exercise of each topic, the exam is very easy. So everybody that devotes time to do one exercise passes. Then determining whether this translates left or right, or whether this slope is high or not, is what has meaning for this particular problem. And well, if you read logistic regression, then this shape is approximated by some exponential of some stuff divided by 1 plus this exponential, whatever. But okay, the details on those exponentials are not really that important. The important thing is that the shape fits what I expect for my particular problem, even if, your statistical book will put a lot of text on odds and whatever. It's kind of, this is a nice shape for my particular problem, so I choose it, and then I try to fit this shape to my data. So my model output is that if you study 20 hours, you have 18% chance of passing. If you study 100 hours, you have 90% chance of passing. But the issue is, how do we fit the data? Well, which is the cost function? Because in the deterministic setup, okay, each failure has 2 or 7 error, and you minimize that. It was really understood. But in the probabilistic interpretation, well, this student and this student studied basically the same number of hours, but one failed and the other not. Then is there an error in my model? No, I mean, it says that, the likelihood of passing seems to be high, so it's kind of bad luck. So the errors need to be considered in a different way. There is no such thing as error, but in this case, these models work with what is called maximum likelihood estimation, in the sense that if this is a conditional probability, then okay, maybe if I have samples x1 0, x2 1, x3 1, x4 0, and so on. And then, well, if this is the conditional probability, then okay, the probability of this thing happening will be probability of 0 given x1, and that will be 1 minus f of x1. Probability of 1 given x2 will be f of x2, etc. And then if we assume that samples are independently drawn, let's say from whatever random distribution happens to govern this pass-fail stuff, then the probability of having the dataset 0, 1, 1, 0 is the product of these probabilities. So my loss function somehow this f actually depends on the theta parameters. I was disregarding that this f was adjustable 1 minute ago, but now, whoop, I recall that, no, f is actually adjustable. Then I, put this red theta there. So x1, x2, x3, x4 are, fixed data points, and then I must theta so that the product of all these things must be maximum. Then this is called the maximum likelihood approach. But, when you multiply many numbers smaller than 1, then you get a very small number, are for numerical precision issues, and well, some other information theoretical stuff that maybe don't know, but forget about it for the moment being. For numerical issues, let's say, instead of working with numbers that range to the 10 to the minus 64, we work with the logarithm. So in many cases, we maximize log likelihood of samples, and this is the abstract way of setting up the problem of obtaining this blue shape telling me the probability of passing as a function of study time. And in this case, f was something like this, but don't be afraid of the exponentials. It's just some handy stuff to synthesize this shape, which was what we intuitively thought it was good enough for my problem. So let's summarize the classification problem statement and end this video. In the previous video and in this one, we discussed the meaning of what was fitting a model that, given an input, gave a certain output, and we needed to fit some of the parameters of that model. And the output to fit, let's say, was binary labeled data, yes, no, dog, no dog, or whatever. So we had sort of ideal, perfect classification rules, so that if some function is positive, then it's a dog. It's negative, then it's not a dog. But, in some cases that problem was not unique, and we needed to find somehow the smoothest function that did the job. And in other cases, if f was too simple, then perfect classification was not possible, and we needed the concept of loss function, maybe non-symmetric. But now we were discussing a probabilistic interpretation in which the goal was not a yes-no answer from my model, but a probability of some event occurring. But of course the data was yes-no, so we needed to do some kind of product of probabilities and maximize that. Then we have maximum likelihood or maximum log likelihood. But it's also true that the probabilistic and deterministic options are somehow closer than it may appear, in the sense that, okay, if I am classifying in a deterministic stuff dog, not dog, then maybe instead of looking only at the sign of whatever function, if some classificator told me 0.95 confidence, let's say, that it's a dog, or 0.05 confidence that it's a dog, then that may be helpful for me to know how sure I am about my output. So even if my dog problem is deterministic, that's why I named it, say, confidence and not probability. But that number may be useful. So as I say here, in some cases, I wishfully may cast a deterministic problem as a probabilistic one and require my model a numerical output that I can examine to see how confident my model was on its output. So this is one relation between deterministic and probabilistic stuff. And the other is that, okay, I may first train a probabilistic model, but then later on I may set a threshold saying that, okay, I am telling my students they must study more than 80 hours, and I am going to put homework so that they actually need to devote those 80 hours to my course. Then the amount of homework you put as a threshold that, if you don't do that homework, don't come to the examination, it's kind of a binary threshold, yes, no, based on a probabilistic model. So either you can have the dog problem in which you want a number to say how sure you are about this being a dog, or you have a probabilistic model, but you need a binary thing that, okay, if this component in blood test is larger than 0.93 milliliters, then you take this pill. Then, binary to probabilistic or probabilistic to binary are kind of contraptions we can make in order to better solve our practical problems. Of course, the mathematical theory on statistics or on function minimization or whatever is what it is, the axioms and theorems, but how we, the engineers, use those tools is up to our wise choice for each application. So good, we finish here. Thanks for watching.